George, who is a PhD student in astronomy and a CSE fellow at the University of Illinois at Urbana-Champaign. He's currently a research assistant in the gravity group at NCSA, member of LIGO experiment, NanoGrav, and the DES collaborations, and an LLST data science fellow working at the interface of deep learning, high-performance computing, and gravitational wave astrophysics. So let's welcome Daniel.
Okay then, good afternoon everyone. So I'll be talking about a bunch of deep learning techniques for doing gravitational wave analysis. So 100 years ago, Albert Einstein came up with this general theory of relativity. This showed that gravity is the curvature of space and time. So space-time can be thought of as a rubber sheet, and this can stretch and squeeze, and that can actually produce this force called gravity. So an implication of this theory was the existence of gravitational waves. So these are ripples in the fabric of space and time. As when really dense objects like neutron stars or black holes, when they collide, these create these ripples, and these ripples cause space to stretch and squeeze. So if a gravitational wave passes through you, you will be stretching and squeezing in perpendicular directions. So these signals are really weak, so it's really hard to detect them. But a couple of years ago, the LIGO, the Laser Interferometer Gravitational Wave Observatory, observed for the first time these gravitational wave signals from the merger of two black holes a billion light years away. So you can see this is the shape of a gravitational wave signal. It looks like a sinusoidal waveform with increasing amplitude and frequency. So now we have two gravitational wave detectors in the US, one in Hanford and one in Louisiana. And recently this year there's a third one in Italy called Virgo that's now active. And now that we have all these gravitational wave observatories, this is turning into a routinely, it's turning into an observatory that will routinely have these observations of exotic astrophysical events. So we have already detected many binary black hole mergers, and these are in a different parameter space. So based on X-ray studies, we observe black holes with much lower masses, and we have detected these really massive black holes, and this is like the first observation we have of these events. And then a month ago, 2 months ago, we announced for the first time the observation of two neutron stars merging. And this is much more interesting than black holes because these events, when matter merges, you actually detect light. So observers, like astronomy, every astronomer observed these events from gamma rays, X-rays, UV light, all the way up to radio waves. So this was like one of the most interesting events of this year. And this actually solved a lot of mysteries. We found out how all this gold and platinum is actually produced from these events. And the Nobel Prize in Physics in 2017 was awarded to Kip Thorne, Ray Weiss, and Barry Barish for leading the LIGO collaboration. And the award ceremony is actually going on today. So this is really exciting, but there are still a lot of challenges. You can see that these are some time series and the corresponding spectrograms of data from the LIGO detectors, and it's really hard to detect these weak signals. So gravitational wave signals are so weak that it's like 1,000 times smaller than the width of a proton. So can anybody tell me which one of these four waveforms contain a signal buried in the noise? So it's really hard. So this is the solution. You can actually see the first and the last one actually have a very weak signal. So it's not visible in the time series or the spectrogram. So how do you detect signals that are so weak? Well, you want to do a classification and then a regression process. So you want to detect a signal, which is classification, and then you want to predict the parameters of the source of the signal. So for really weak signals like these, what we can do is that we can solve Einstein's equations on supercomputers like Blue Waters for every possible event. So at NCSA, in our gravity group, we actually do a lot of these simulations. So now we know what gravitational waves should look like. Since we have this information, we can actually extract signals from very noisy data sets where the signal to noise ratio is much less than 1. But even then, so you have a bunch of these templates that you get from simulations. So now you need to find these in the noisy data sets. So you can think of an analogy. You want to find cats and dogs, and you have a huge album of these cats and dog photos. So what LIGO currently does is a template matching technique called match filtering, where you compare every second of data with every one of these templates. And there's like 100,000 of these templates, so it's a very computationally intensive problem, and you cannot actually look for all possible signals because of the computational costs. So how do you solve this problem? Well, for image processing, people have found out that you can actually train a neural network and then teach it to look for these cats and dogs. And in a similar way, we are applying this to time series data. We take all these templates that people use for match filtering, and then we train a neural network once. And after this one-time training process, the data analysis can be carried out really fast. So you all know deep learning, so I can probably skip this slide. But yeah, basic idea is you combine a bunch of neural networks, have very deep layers, and you can do end-to-end processing on raw data, and can automatically learn all the required features. What we actually do is to use convolutional neural network, one-dimensional convolutional networks for doing both classification and regression on these noisy time series inputs. And there are a lot of advantages. You can feed in the raw data, and it can automatically learn the optimal strategies. You can use optimized hardware like GPUs and FPGAs to actually do the analysis on the detector. You don't actually have to transfer all this data to a remote cluster. And deep learning can automatically learn the characteristics of noise in the LIGO detector. So it's resilient to all these anomalies and glitches that occur really frequently. And even though the training data, where you have thousands of templates, is like gigabytes of data, the neural network actually learns to compress all this into a few megabytes. So it's actually learning patterns about the waveforms rather than just memorizing the templates. So here, this is one of the 1D convolution networks that we use. We just randomly tried up to 4 convolution layers, and we just did a hyperparameter sweep. And we designed 2 networks which are very similar. The first one is a classifier. It tells you if there's a signal or not. And if the classifier says yes, then you have a second network with a similar architecture that will predict the masses of the black holes that produce a signal. So it's a set of 2 neural networks. And we separated it into 2 sets because you can have the classifier have additional classes for different kinds of events like neutron stars, black holes, or even glitches. And then depending on the class, you can create a different predictor network for estimating the properties of that particular event. And we use dilated convolution layers. So and then for training, we actually took real data that's publicly available. We injected templates into the real data, and we trained the network on these data sets. So you can see the real data is not perfectly Gaussian. It has a lot of glitches as shown in the spectrograms. So the network has the advantage that it can learn to deal with these non-Gaussian noise, whereas the match filtering technique is optimal only for pure Gaussian noise. And now we compare the accuracy of detecting signals on the same type of events that it was trained on. And we can see that it achieves nearly the same accuracy as doing the match filtering method. And this has a false alarm rate of less than 0.6%. And the advantage is that once the network actually detects a signal, you can then verify it using match filtering. So you're not losing any statistical information. Just you can reduce the number of templates that you need to search for. And we achieve 100% detection sensitivity when the signal to noise ratio, the optimal match filter SNR is greater than 10. And then we compare the error in predicting the masses of the black holes, and you can see that it's more accurate than match filtering because the neural networks are able to interpolate to points between your template banks. So it's basically like an interpolating function. Whereas match filtering, you look for the exact template.
Is that a simulation label?
No, so we are injecting templates into the real LIGO data stream and then predicting what the error is in measuring the properties of these templates. So here you have solutions that you get from solving Einstein's equations. Those are the gravitational waveforms. Then you take real LIGO data, you inject it, and then you see how well you can recover these signals. Yes, it's additive noise. And for very high SNR, we actually found that we can get the mean relative error less than 5% for SNR of like 100. Whereas match filtering, based on the same training templates, the minimum error that you can get is like 10% because the template bank is not infinitely sampled. And then we fed the same highly noisy time series data without doing any manual feature extraction to a bunch of traditional machine learning methods, and we found that neural networks, unlike these traditional methods, can actually deal with the very noisy data streams. So for both detection and parameter estimation, we got much better results. This is not really a fair comparison because you can actually do manual feature extraction to improve the accuracy for all these methods. But here we just did a naive attempt by feeding the same time series as the features. And then compared to match filtering, on the same CPU, after training the network, we get over 100 times speed up of doing the inference. And then if you actually do a GPU, you get like 5,000 times speed up. And you can actually, we did not do any techniques to actually optimize the network even further by like pruning unnecessary neurons and things like that. But this still is so fast that you can do analysis in real time as the data is streaming from the detectors. And another advantage is that LIGO has a lot of glitches. So sine Gaussian glitches is what's frequently observed in these LIGO detectors. Its sources are not known. So we tried injecting a bunch of these glitches which are not signals, and then we found that the neural network can still differentiate these glitches from signals. So the false alarm rate in the presence of glitches is less than 1%. Whereas if you do naive match filtering, then when the glitches have the same frequency as a template in your template bank, there's a high match filter output. So it thinks that it's a signal, whereas with the neural network, you can train it to distinguish things which are not signals. So this is an advantage of applying deep learning here. And another really interesting thing that we found was even when there's a glitch that happens in coincidence with a signal, the neural network was still able to detect it. So we trained it on some examples, and then we found that we recovered 80% of signals injected during a new glitch from our test set. Whereas with match filtering, it's not possible to distinguish a signal when it occurs at the same time as a glitch. So for the recent discovery of neutron stars, there was actually a glitch at the same time as the signal in one of the detectors, and the automatic pipeline missed this. And a grad student actually looked at this spectrogram and found that there was actually a signal behind this glitch. So with this deep learning approach, we can automatically do these detections. So here we actually have a demo that we showed at the supercomputing conference 2 weeks ago. We did this with NVIDIA. So you can actually see what each layer of the neural network is doing. So you're sliding the network through the data, and this is a simulation of what the event should look like. And this is real data from the LIGO detector around the first gravitational wave event. You can see that the first convolution layer is actually acting like a denoising filter. There's nothing output in the second layer unless there's actually a signal. So now there's some activity happening in all the layers, and now it says that the gravitational wave is detected and these are the masses. And then finally we tried testing the network on signals that it was not trained with. So we trained with black holes without spins and on quasi-circular orbits, and now here is an eccentric black hole signal which occurs from elliptical orbits. And here we can actually see that the network was able to detect these kinds of signals with the same accuracy as our original training type of signals. And this is because networks can generalize, whereas this template matching techniques cannot. So there are a couple of papers showing that template match filtering methods will miss these highly eccentric signals. And we showed that we can actually detect these. So the advantage of doing all this is that once you detect a gravitational wave signal, you can immediately, with all these gravitational wave detectors, you can pinpoint where the source of the signal is, and then you can turn your telescopes around and immediately see the electromagnetic counterparts from these events, and also we might be able to detect astroparticle counterparts like neutrinos. So this is like the real-time multi-messenger scenario, which is like going to lead to really groundbreaking discoveries in astronomy and astrophysics. So at NCSA, we're actually working on applying deep learning to different parts of these multi-messenger campaigns, where you have gravitational wave detectors. We are applying it to nanograv and ELIs in the future, and we are also trying to train classifiers from telescope data such as DES and LSST in the future, and apply deep learning classifiers to actually find this electromagnetic counterpart in real time. So what we are doing is to take simulations of Einstein's equations and then train these machine learning methods, then use GPU so that you can analyze the data much faster than with the current techniques. So let's see, since I think it's time is up, so any questions? So I just wanted to add, I have another poster on a related topic as well on finding anomalies in LIGO data, so you can come by and ask if you have any questions. All right.
So your technique is robust against glitch.
Yes.
But it's also able to detect exotic signal.
Yes.
What your trick there? Because did you use the glitch in the training?
So we use real data, which contains some glitches in the training set, but then we applied it on new types of glitches, and we found that the network can distinguish them.
Fundamental difference between a glitch and
Oh, so
exotic signal.
So if you show a human the signal, they will obviously know that this is a gravitational wave because it has a characteristic of increasing frequency and amplitude. Whereas a glitch will look something completely different, like it might look like one of these, which if a human can actually distinguish these from signals, and the same way the network is able to do that. Yeah.
So how large is your data, your training set? Because it sounds like you have to simulate a ton of training data because of massive computing.
Yes.
You have to simulate with almost a very fine grain.
Yes. So these templates are already being used for match filtering. So we already have a lot of simulations that we can use. So currently match filtering pipelines, so what they do is they have some high performance simulations, and then they fit models to it to actually generate more data in intermediate parameters. So by combining both the semi-analytic methods and the full numerical relativity simulations, you can generate a lot of data to train these networks. And I also wanted to mention that you don't have to trust the predictions of the networks, because once you know what the masses of the signal is, you can do traditional template matching with those parameters to actually estimate all the statistics and to confirm that event and measure the significance and signal to noise ratio, distance, and other parameters. So it's like accelerating the existing pipelines by giving an initial guess. Yeah.
Is there an upper bound on the highest eccentricity that the could detect?
Yeah, so for detecting, we found that like even when the eccentricity is like very large, like 0.5, it's between 0 and 1, but when it's 0.5, we could still detect almost at the same sensitivity. But for very highly eccentric, like 1, which will never occur in nature, we couldn't detect it because it looks completely different. It doesn't look at all. It will be like highly modulating.
What about something like 0.99?
I have to check. I don't remember the numbers exactly, but in practice, the signals will be moderately eccentric, like less than 0.4. So those kinds of signals we could detect with the same sensitivity. Yeah.
Since my understanding is you're giving it the raw waveform and not doing any kind of sort of Fourier or wavelet.
No.
Since it's so easy to see the signal in this sort of frequency domain, is there some reason that you don't, while you're sliding your filter, you don't also give it some, just that kind of spectral?
So you can see that so we tried spectrograms. You can see that the spectrograms don't actually, it's not visible when the signals are really weak. So spectrogram is a lossy representation because you're averaging over bins, and then it's non-invertible. You're losing some phase information. So
You can keep the phase information.
yes, you can. But we found that directly by feeding the time series data, we got really good results, and we couldn't get the same accuracy when we fed these spectrograms. But there might be ways to actually keep additional information in spectrograms and try it. But neural networks should be able to do these internal internal computation of frequencies, right? So we thought we'll just leave all the computations to the networks, see what happens.
I think we have time for one more question. There's any?
Yeah.
How did you decide when it's sliding over the window, like where in the window you consider the real values to be focal point? So like the window's sliding over the signal in a demonstration you showed.
Yeah.
And it's outputting values as it slides through the
Yeah.
You decide like this is the point at which I realized that these values were the real one, not when I was earlier in the window, when the window was earlier or later.
So in the demo that I showed, you can actually see that there are two networks. So one of the networks is actually telling you that there is a signal. So the output of the first network is shown below. So when it actually reaches the signal, it will tell you, okay, now there's a signal. Is that what you meant?
Okay, so we'll let it run for a second.
So the output of the first network, the classifier, is shown below.
Yeah, okay, so
Yeah.
like right now it's spitting out
Yeah.
simple numbers, right?
Yeah, so what we do is we have now two detectors. This is just showing one detector data. And then when we have two detectors, we check if these numbers match exactly. If they don't, it could be.
Okay, what I'm asking is over that time
Yeah.
it output many, many numbers.
Yeah, but these numbers are very close to the actual value. It's within the error bars that LIGO gave in the 90% credibility level. So once you get this number, then you can do the match filtering with those templates having between 32 and 36, so 38 solar masses, and then you can easily find the exact location and the correct value. So we're not like replacing the whole match filtering pipeline. Yeah. Oh, so these signals that we are considering here, the binary black hole mergers, are typically less than 1 second long. So we just arbitrarily chose a 1 second window, but we could have trained it with any length. And there's actually a poster here on showing you can use fully convolutional networks to have arbitrary length inputs. But with the 1 second window works really well for these signals. And it's very fast that sliding through the data can still be done in real time. It actually takes like a 500 microseconds to evaluate this network on 1 second of data. Yeah.
Let's thank Daniel again.